Now that we know a few extra properties of the Dirac delta and the convolution, let's see what we can figure out about the sort of general behavior of second-order linear differential equations. What we're going to do actually works for any order as long as your differential equation is linear. But we're going to work with second-order equations just because we're sort of familiar with them. So to start out with, let's find the impulse response of a second-order system. So the impulse response is just the solution that you get if your forcing function is just the Dirac delta. So the idea with calling this the impulse response is our system, right? I have the way I have this notation set up is that it's as if we have a mass spring system with a damper, and initially it's just sitting there, hanging motionless at its equilibrium position, and then we come along and give it a tap at time 0, right? This delta is 1 unit of impulse, so we're just giving this a unit tap at time 0 and watching what happens. So let's find an expression for the impulse response. Well, the impulse response is the solution to this differential equation, so we can find a formula for the impulse response by putting the impulse response in here, right? Assuming that it is a solution, because by definition the impulse response is a solution to this differential equation. So we're going to plug in the impulse response, which we don't know yet. And then we're just going to solve this differential equation. How do you solve this kind of differential equation? Well, use the Laplace transform, of course. So take the Laplace transform on both sides of the equation. On the left-hand side, we get m times, so Laplace transform of the second derivative of the impulse response. Because of the initial conditions, the only term of the Laplace transform of the second derivative that survives is s squared Laplace transform of the impulse response, right? The two terms that you get for y of 0 and y prime of 0, those are both 0, so they disappear. Plus beta times Laplace transform of the first derivative is s times Laplace transform of y sub impulse response, again because the term that involves the initial conditions is 0, plus k times Laplace transform of the impulse response equals Laplace transform of delta. But remember, the Laplace transform of delta is 1, the unshifted delta, right? In general, the Laplace transform of delta with a shift is e to the minus ct. But if your shift is 0, then this is just e to the 0, so it's 1. Okay. So now we're solving for the impulse response. So let's factor out. On the left-hand side, let's factor out the impulse response. We get ms squared plus beta s plus k times the Laplace transform of the impulse response is equal to 1. And so the Laplace transform of the impulse response is 1 over ms squared plus beta s plus k. And so the impulse response itself, we just take inverse transforms. So the impulse response is the inverse transform of 1 over ms squared plus beta s plus k. Okay. And if you had particular values for your system, for your mass, your damping, and for your spring, you could actually work out what this inverse transform is. Okay, so that's an impulse response, but now let's back up and ask a more general question. If we know an impulse response, what is the solution given any sort of forcing here? So I guess, well, how do we solve this kind of differential equation? Well, we take the Laplace transform. So on the left-hand side, again, I'm going to have initial conditions being 0. If the initial conditions aren't 0, we know what happens, right? Changing the initial conditions just adds a complementary solution, or one of the many complementary solutions. So changing the initial conditions actually doesn't really do anything interesting. So let's solve this differential equation where the forcing is completely arbitrary. I guess except that it should be piecewise continuous at least. Okay, so take Laplace transforms on both sides. As usual, all the terms involving the initial conditions drop out, and we get ms squared Laplace transform of y plus beta s Laplace transform of y plus k times Laplace transform of y equals Laplace transform of f, which, we don't know what f is, but whatever it is, the Laplace transform of f shows up on the right-hand side. Then, as usual, factor out the Laplace transform of y. So ms squared plus beta s plus k Laplace transform of y equals Laplace transform of f. Okay, so Laplace transform of y is 1 over ms squared plus beta s plus k times Laplace transform of f. And this is multiplication right here. And now we take inverse transforms. So y is the inverse transform of 1 over ms squared plus beta s plus k. Incidentally, this function right here, you might have noticed that when we did this calculation, this function actually only depended on the mass spring system that we started with, on m, beta, and k. And so it doesn't depend on the forcing at all, right? The effect of the forcing is isolated to this term over here. So this function depends only on the system, and it's called the transfer function for the system. So the transfer function doesn't depend on the forcing at all. And we'll see that as we're about to see, so when we take inverse transforms, we get inverse transform of the transfer function times the Laplace transform of f. But the convolution theorem says that a product in the S world is a convolution in the T world. So we get the inverse transform of 1 over ms squared plus beta s plus k. So this is the inverse transform of the transfer function, also known as, right, this right here is actually the impulse response, convolved with the inverse transform of the transform of f. So y itself is the impulse response convolved with f. So the solution to this differential equation that we started with is actually, it's easy to write down as a convolution integral. And in fact, this is sort of, it shouldn't be a surprise that we get this formula, because this is kind of how we invented the definition of convolution, right? Convolution is some sort of sum over the past of the current effect, right? The convolution just takes all of the past. At each point in the past, it figures out what is the current effect of that in the past, and it adds up all of those little contributions from the past. That's what the convolution does. But that's sort of exactly what a second order system is doing, right? It has all of this forcing that's happening at different times. This is all of this forcing at different times. This is impulses happening at times in the past. And so to add up the effect in the present of all of these impulses that happened in the past, you just do the convolution, which is how you add them up, right? I guess maybe the final point here is that these are impulses because f is the same as f convolved delta, right? So f is sort of telling you the strength in the past of each impulse. All right, so there's this really nice expression for a solution for arbitrary forcing. It's just the impulse response convolved with the forcing. This is kind of a surprise. I think it's a nice actually, I'm going to turn this around. right? The convolution is commutative, so I can turn this around if I want. It's kind of a nice exercise to plug this back into the original differential equation and see that it actually works. So remember, the original differential equation was my double prime plus beta y prime plus ky equals f. It's really f of t, but I'm going to be lazy and just write f. Okay, so let's plug this into this differential equation and see that it actually is a solution. So when we do that, we get m times the second derivative of f convolved with the impulse response plus beta times the first derivative of f convolved with the impulse response plus k times f convolved with the impulse response. And we want to know, is this equal to f? Okay, well remember we worked out a formula for what the derivative of a convolution is. Since the impulse response at 0 is 0, and the derivative of the impulse response at 0 is also 0, sort of. I'm sweeping a little bit under the rug here, but since these are both 0, those boundary terms that we got when we differentiated a convolution, those boundary terms are both 0 because of this. So we only get the term that has the derivative on the second piece. So we get m times f convolved with the second derivative of the impulse response plus, and then the same thing happens for the second term, beta times f convolved with the first derivative of the impulse response plus k times f convolved with the impulse response. And again, we want to know, is this equal to f? Okay, well, remember one property of convolution is that it's linear, so we can actually sort of factor all of these f convolved with outside like this. And what we're left with inside the parentheses is m times second derivative of the impulse response times beta times first derivative of the impulse response plus k times the impulse response itself. And remember, we want to know, is this equal to f? Well, to know if this is equal to f, we need to know what is this stuff in parentheses. But remember what we mean by impulse response. The impulse response, just by definition, is the solution to the equation my double prime plus beta y prime plus ky equals delta, right? And inside this parentheses, we have the left-hand side of this differential equation. And so that means the stuff in parentheses is just equal to delta. And we want to know, is that equal to f? Well, f convolved delta is f. So this shows that our formula for the general solution here really is a genuine solution to the differential equation, which is maybe a bit of a surprise since it looks so simple, but in fact, it works.